All right. Thank you everybody for coming to today's workshop, 7 tips to make your data management life easier. I'm Jeremy Kenyon. I'm a research librarian here at the University of Idaho. I'm also the library's liaison to the College of Natural Resources. And I'm working on a project with others in the library on something called the Data Hub, which I'll mention in just a moment. I guess just a kind of point of order, if you have any questions or anything, just put it in the chat. And we've got somebody, Jessica Martinez, who's looking after that, and she'll be able to make sure that your question gets asked. Towards the end, we might just open it up to general Q&A, and then at that point, if people want to unmute and ask questions and so on, we're happy to do that. So just raise your hand or pop your question in the chat, and we'll be happy to get to it. So we're going to take you through kind of our 7 tips, or my 7 tips for data management. We'll talk a little bit about the Data Hub right here at the beginning, so you know what's coming, and then we'll have some time for some Q&A. For those of you who haven't heard, and that's probably most of you, the library is launching a new service fairly soon that we're calling the Data Hub, and this is geospatial and data sciences support. So currently on campus, there's not really a great place where there's a staffed desk to answer questions about working with geospatial information or data sciences information that is a sort of consistent service that somebody on campus here provides. And so on the first floor of the library, in the map room, which is just right over there, if you've been here in the library, we'll have a whole bunch of things set up pretty soon. We're actually in the process right now of getting furniture and equipment and everything else set up. We'll have web content to support it. But a couple things to think about. We'll have individual workstations for specific kind of research software. The tools and exactly what those are going to be has not quite been decided. So if you have any suggestions or requirements, just let us know, get in touch with me. Let us know what you'd like to see there. We're going to have collaborative work areas for people who are working in groups. And then we'll have that service desk that's going to be staffed by me, by our GIS librarian, by our infrastructure librarian, who's also our engineering liaison, and some others. And so we've even encouraged other groups on campus, including research computing and data services, to join us. And they've been positive about doing that. So the hope is that in the fall, not only will you have people from the library, but you'll actually have people from other campus units sitting in there as well. And so it becomes a one-stop shop for getting help on all of these kinds of questions. So the website is on there. It's possible that it'll be open this fall, but we're shooting definitely for a spring 2022 opening. So after Christmas, hopefully it'll be a pretty great place to come and get help. Okay, with that in mind, we're going to get to the actual 7 tips for today. And this is aimed at the graduate student level. This is aimed at anybody who's interested in the topic. But it's really also aimed at people who are getting into data analysis and research, or people who have been working and are frustrated with some of their processes. And hopefully you'll get some tips out of this that'll be helpful to you. And so tip number 1 is one that we all have heard, but many of us don't actually follow through with very effectively, which is back up your data. A lot of us have common kinds of problems that have occurred to us over the years. Data has been corrupted. We've lost our laptops or our equipment. We make mistakes, so we accidentally delete stuff, or somebody who's working with us makes a change that turned out to be a mistake. These kinds of things happen all the time. One of the things that you can do to kind of deal with these kinds of issues is follow the 3-2-1 rule. And so the 3-2-1 rule, as you can see on the screen, you want to have about 3 copies of your data, one that you're working on, and then the other 2 that are considered backups. You want to have your data on at least 2 different types of storage media, and you want to store one of these on offsite storage in some way. So actually, this is a lot easier than it sounds if you keep your data in some kind of a cloud storage device. So you use OneDrive, you use Dropbox, Google Drive. You've essentially got 2 copies immediately. You've got your local copy on your computer, and you've got your copy in some data center it's replicated to somewhere else. And so that also gives you an offsite storage location. And then all you just need to do is use a USB or an external hard drive, something consistent, and create a third copy of it. And that third copy can be located elsewhere. So if anything happens to your computer in any way, shape, or form, really, you'll be able to get your data back either from that external copy or from the cloud server down the road. So I understand that in some cases your data is too big, too complex. Cloud systems have problems at times with synchronizing. And so this doesn't necessarily work for everyone. And in those cases, you should probably pursue some other kinds of approaches, which we could talk about if you had questions about it. But for the vast majority of people, this kind of an approach should work. Most data is usually in a spreadsheet form, and most data is usually in a relatively small megabytes to gigabytes, low gigabytes kind of volume. So remember to back up your data and follow the 3-2-1 rule to do so. Tip number 2 is to try not to modify your raw data if at all possible. And after you do that, make sure you version your derivatives. Or after you refrain from modifying your raw data, version your derivatives. So what does all this mean? So on the screen here, you'll see an example of a typical kind of process. Somebody had a couple of data sets, temperature and salinity data. They work through these different stages, and their data set kind of takes on different forms of different processes or at different stages through the process. And each time in the example you're seeing, they're creating a new data set. So you're copying that data set or you're importing it into the system, and then you're saving it as a completely new file so that you are maintaining this record over time of different versions of your data so that you can always go back and you can always get back to those earlier data sets if you need to for some reason. And it's very possible that you're exploring as you go through this, and you might want to go back and try something else, do something else. And so this process of copying and saving is a good approach. Along with that, you may just want to write protect the original data itself. And so that's actually a very simple thing too. On a Windows machine, you just right click on the file, you bring up the properties, and then you select read only. And so if you make your data read only, you can't accidentally modify it. So you might do that to raw data whenever you've got it in there. It's a pretty useful way of thinking about it. There are other approaches to versioning your data. One of the examples is put forward in this paper called Good Enough Practices in Scientific Computing. And they actually have an interesting idea of just copying the entire project contents over and over again and saving it. And so what you can see on the screen here is under a folder where everything is in that project name, you have a current folder, and that's where you're working. And then just periodically, you'll copy the current folder and you'll paste it in, and then you'll change the name to whatever the date is. And then that will just be a record of everything you've done. And so their argument here is that data is cheap and time is expensive. And so again, if you're dealing with relatively small data, if you're dealing with data that's not very difficult, or that's not much of a burden on your hard drive, then there's really no cost in replicating the data like this. It creates these other versions of basically all of your files, including scripts, including documents. So it's a pretty good approach if that's useful to you. And if you get really fancy and you're comfortable with scripting, you could automate this process. So it's one click or one entry on the command line, and it'll just automatically create your copy and you go on with your work. So it's a way to think about it. But either way, you want to make sure you version out your data so that you don't end up rewriting an existing data set over and over and then losing track of where you're at. So tip number 3 is kind of a grab bag of a bunch of different points. And it's essentially to be intentional with your data values. So when you have a data set of some sort, you have the option of what exactly you're going to put in all those data values, what you're going to call your variable names. And my tip here is just to be intentional with what you're doing. Like, do it deliberately and think about it. And so one of the things to think about is the use of identifiers. And identifiers are often the means of reusing this data later on or standardizing it with other data sets out in the world so that you can use them together. In the example that you see on the screen here, this is a list of articles that was produced by a system. And so one of the types of identifiers you can see in the middle on this column called DOI is a direct object identifier. And this is actually a standardized identifier. It's part of an international registry system. And so it's actually globally unique to this article. And it makes it easier to be able to not only identify which article is which, but it also means that if I have other data about articles out there that I want to pull down, there's a very good chance that the DOI is going to be the factor or the term that I'm going to use on which to select those articles from that other data set and then join them together. And so just think as you're going through about using standardized identifiers. Other examples are species names or language codes, depending on what kind of data you're dealing with. And then also you want to think about local identifiers. So in this table again, or if you look over here on the left, you'll see the index column here. And the index column works as a record ID. Every single row is unique to every other row in this data set. It just goes from 0 to whatever the amount there is. And local identifiers, they're not globally unique. If you put this data set somewhere else, it would be sort of confused with other things, but within this, it gives us a means to always find this record every single time. And so you want to think about making sure to include those. But part of being intentional isn't just thinking about kind of those global contexts. You just want to think about using good variable names, thinking about reuse as you're working with it. Here's examples of various ways of considering your variable names. One of the common problems that you'll see is people using spaces in variable names when they really shouldn't. Most computation use spaces for other purposes. And so when we create variable names, data values, things like that, if we can, generally keep the spaces out of it. So you see that over on the left where the good names have underscores instead of spaces. Other things you want to think about is having your names be short, but not too short. And so over on the right, you'll see for weight, the one to avoid is using W, period. That can mean all sorts of different things. So it's relatively inexpensive just to type out the word weight and just use that. So there's no reason not to. You want to use variable names that are meaningful and useful, but not too much. And then in a number of other cases, you want to think about both the use of zeros and the use of no data values or blanks or null values. So if, for example, in the library world, if we were looking at something like book circulation, 0 is a value. It means something to say that there were 0 books circulated that day. And so if zeros are values, you don't want to use zeros as either a code in a kind of binary classification of 0 or 1, or you don't want to use it as a simply a filler to like fill something in the space. You want to use 0 if it's actually a number that's meaningful in your data set. In other cases, you don't have a value at all. And so you'll want to think about what to use there. And my recommendation is not to use nothing. You want to use something that's unrealistic for your data set. And so if you have, again, if we were talking about book circulation, we can never have less than 0 numbers of books circulating. We can't have negative numbers. So if I wanted to say this day we just didn't have any value, I might put a -999. And that's just a way of saying, this doesn't make any sense. Just ignore this field. You can also use codes like NA or null. Now this is a little bit controversial. There's some argument that you should actually use blanks because R, Python, SQL, a number of tools will actually read blanks and do something with them. It's not actually too hard for them to use it. And also that using negative numbers can throw off analyses down the road. But I think that's really just a matter of work. You just have to know that those codes are there and then adjust for them before you go into the analysis. So remove them or do whatever it is that you feel like you need to do. And with that in mind, you might consider using other kinds of error codes, which are things that you can just create. They're not necessarily standardized in this case, to help you keep track of what happens if there's no value, or maybe there was an error of a particular sort that you want to note. So you could use -333 or something else, whatever would make sense for you. And with that in mind, I'll move to tip 4, which is you record all of these things in your data dictionary or your code book. And so in order to create a data set of any real value, both to yourself and to other people, you have to have metadata. You have to have it documented, and you have to be saying, like, this is what this column is all about. These are the decisions that I made. This is the range of valid values, and so on. And so all your error codes, your no data value codes, anything like that is going to be put into a data dictionary or code book. There are lots of different types of metadata relevant to a data set. README files are really useful for describing just kind of what these files and folders are about. There are structured metadata files in a lot of different fields, like geospatial data. They have all sorts of rules associated with them, but at the very least, your data dictionary or your code book is your MVP of your documentation. If you use this, you can at least clarify what these things are and how to understand the data set itself. So this is an example from an article. This is another example from a piece about data organization, another example, data dictionary. So it doesn't have to be complex. It doesn't have to be hard. You can do it in another spreadsheet. And all of these kinds of fields that you see are options for things that you might describe in your data set. So you can work through that and figure out which ones are the most relevant. They can be as simple as you see on the screen on line 2. It's just called an animal identifier. But if you wanted to have a whole paragraph of text, you could do that. So at the very least, use a data dictionary, and it'll make your life easier. It'll make the lives of the people who want to look at your data a lot easier as well. Okay, tip 5, be aware of the concept of long versus wide formats for data. And if you've worked in R already, then you're probably very familiar with the concept of tidy data, which is also kind of synonymous with long data over on the right side. But typically we usually run into wide data. So if we look at the column or the image on the left, you'll see that there's a location column here. And then there's a couple of year columns across the top and a bunch of data. And we run into this all the time. Hundreds of years of government statistical reports are written like this. This is a very common and heavily used way. And the reason is because it's useful for human consumption. When we look at this, at least in the West, and in English, we read from left to right. So this actually just makes sense. We can see the progression of time. It's a pretty straightforward way to do it. And there's nothing wrong with using a wide format as long as you're using it in the right context. And so these are really good for final outputs for people to read. If you're going to put a report in front of somebody, a wide format's fine. You put this table in an article. It makes perfect sense to do it. But if you're going to feed your data into a machine of some sort, and when we use the word machine here, we mean any kind of computational program. So this is an analysis tool. This is a visualization tool. If you're putting it into a database, tidy data or long data formats are preferred. They're preferred by the machine, even if for you and me, it's a little bit harder to read and understand what we're looking at. Tidy data, to just kind of summarize, if you've already heard this, then this will be something you know, but if you don't, it basically dictates that you should have a single variable per column. So over here on the left, we have a year stretched across 3 different columns, but over here we combine it all into a single column. So year is one column, location is one, and then the count is one. And then you want to have one observation per row. And so this is one observation of these variables per row. And then also you want to have one data value per cell. So we don't want to combine a bunch of concepts inside of a single cell. In this case, it's pretty straightforward. But that's tidy data in a nutshell. And so there are lots and lots of tools for reshaping data to long and wide. If you use R and Python, there's some pretty standard techniques for doing it using tidyr or pandas. You'll see those on the screen: gather and spread, pivot and melt, depending on the tool that you're using. But if you're using kind of just a general analysis tool of other sorts, SPSS, SAS, Stata, Tableau, Oracle Analytics, and others all have features for reshaping data. So there may be a prepare data section like early before you get into whatever else you're going to do with it. And that's essentially your mechanism for reshaping the data before going into the process of analysis. So the issue here is just to be aware of these two types of formats, and the idea that you want to think about, is this for human consumption or is this for machine consumption? And if it's for the machine, if it's for analysis or visualization or processing, put it in tidy format. That's going to be a better way to go. All right, tip number 6 is to use standardized date time formats. And so this one is something we probably all run into in some form or fashion. It's especially if you've ever typed dates into Excel and then had Excel like change them on you and do a bunch of things. You end up with something that looks a little bit like this table here, where you've just got all of these different types and ways of formatting data. And so what is the right one? What is the one that works? And one of the issues to consider is it's not just that these are inconsistent, right? So we always want our data values to be roughly in the same format or consistent with each other. But often systems will not necessarily know how to read this string of text. So if you type in, for example, in column C there, Wednesday, July 2nd, 2014, and your system isn't quite engineered in such a way to make use of that, it may just say, I don't know what this is. It looks like a string to me, and throw quotations around it and treat it like a word. And as far as it can tell, that's what it is. In other cases, you may have a system, and Excel's pretty good at this, to be honest. It can kind of figure it out based on enough experience and practice. And so there's an international standard for displaying dates and times. It's codified as something called ISO 8601. And this is the standard date time format that generally you should use, if at all you can. And in most cases, if people are using data that's coming out of an instrument or a platform or some kind of data logger out there, then it's going to automatically produce dates and times in this format. But if you're doing things manually, you might have to discipline yourself to follow this procedure. And what's cool is tools are built to understand this format. So if you look at, for example, the third one for complete date, where it's got the year, the month, and the day there, there's a very good chance that any tool that you give this data to will be able to do kind of derivative functions. So for example, I could say, let me create a column of just the day of the week that corresponds with this. And it can calculate that based on seeing the datetime format. So it recognizes the structure, and then it can do a bunch of other stuff it's designed to do based on that. So whenever you use dates and times, follow this format. It covers basically the extent of our date and time system. And so you should be able to cram almost anything into this standard. All right, so tip number 7 is to assume others are going to see your data. And the basic idea behind this is that data publishing, data sharing, you hear about reproducibility and open science all the time. And all of these are reasons why people are going to want to see your data. And if you get a grant from a federal agency, it's almost expected anymore they're going to require that you share your data through some form or format. Most journals, when you publish, especially in the sciences, are going to expect data sharing. If you're on a team and you've got colleagues and advisors who are going to want to see your data, there's lots of different kinds of cases where people are going to want to see it. And so you should act from the very beginning as if somebody's going to look at your data and see what you're doing and evaluate that at some level. And so all of these things that we've talked about, doing good documentation, backing it up, being intentional about your data formats, your variable names, all of that is absolutely critical to just making sure that what they end up seeing looks solid, right? They may or may not have opinions about the actual value of it, but they will fully understand what they're seeing and be able to make sense of it. So there's no reason that publishing your data or sharing your data should cause anxiety or fear. A lot of people seem to have those kinds of feelings, that data is seen as this idiosyncratic thing that is mine. I did this and you get to see the report at the end. But if you maintain good practices, or as the paper said it, good enough practices during your data management, then you should be in a pretty good place to say, yeah, here it is. You should be able to understand it. It should all make sense, and everything should work pretty well. So just as one example of this, this was published as a letter to the editor just a few days ago in Nature Medicine. And it was about somebody basically dealing with the questions about the evidence base for the drug ivermectin. But the point I just want to raise here is that they are requesting data from the author. They're trying to find out and look deeper at those kinds of analyses. So if your work is going to have an impact of any sort, of any kind, somebody's going to want to take a look at it. And so thinking through those practices, thinking through how to make sure that your data is managed well is a pretty critical step in making sure that if this ever happens in work that you're doing, it's not really that big of a deal. You can show it and you can be confident in the quality of your data. So to kind of summarize all of those things, you know, all of these are useful things to consider in the course of a project. Back up your data using the 3-2-1 rule. Don't modify raw data and version your data as you go. Be intentional with your data values. Think about the process ahead of time. Use a data dictionary or a code book at the very least, even if you don't do any other kind of metadata, and it would be nice if you did, at least do that. Be aware of those long and wide data formats, the capacity to switch back and forth as you need to. Use standardized date and time formats. And in fact, I would say not just date and time formats, anywhere you can introduce standardization, try to do that. And then assume others are going to see your data and act accordingly. And hopefully that will turn into a fairly comfortable process. And over time, you'll get pretty used to doing all of these things pretty effectively. So with that went pretty quick, and I'm happy to take questions or chat about anything anybody wants to chat about. I will also point out that we have one more workshop in our series on October 5th dealing with drop-in citation management help, so keep that in mind. And so with that, I'd open it up to any questions from anybody. I'll bring the chat up here on the screen, which I think y'all will be able to see. But feel free to unmute too if you have a question.
I'm going to put the assessment for today in the chat.
Okay, there's also going to be an assessment link coming in the chat.
I'll stop recording and then people might be more willing to ask their questions.
Okay.